Hi everybody. I want to thank the organisers for inviting me to speak here, talk about cosmic shear and dark energy. But before I get going, I want to say happy birthday to KIPAC. Much in the vein of everyone else, KIPAC's given me an awful lot. And the anniversary, the 10th anniversary of KIPAC is a personal one for me as well. It's a timely anniversary. Because I've been affiliated with SLAC for 10 years now myself. I've only been involved in KIPAC for the last 3 years, but for me it's also a 10th anniversary of how long I've been working in the lab. So happy birthday to me as well. So I'm going to be talking about cosmic shear and dark energy. I'm going to be talking not so much about the work that has already been done in cosmic shear, because to me the most exciting prospects for cosmic shear for dark energy is using measurements of the weak gravitational lensing of the universe to constrain models and constrain parameters of dark energy. And this is something that there's been some fantastic work done so far, which I'm going to review briefly, but I really want to concentrate on the prospects for the future, so kind of looking forward to the next 10 years. What kind of work are we going to be doing here at KIPAC? What kind of results are going to be coming out? What can we expect to come up in the next 10 years? So you've heard already today about weak gravitational lensing being used to constrain cosmology through the gravitational lensing by massive objects in the universe, by clusters of galaxies that Anya was talking about. Cosmic shear is a different regime. Cosmic shear can be considered to be very weak lensing. We're talking about a distortion in galaxy shapes of less than 1%, perhaps. And this is lensing rather than by a specific object, rather than by a cluster of galaxies, for example. This is lensing by the universe as a whole, by the mass of the matter in the universe as a whole. And so this is sort of the image that's often shown with this. If you have light coming from a distant galaxy, it's passing through all this structure, all this dark matter passing by all these galaxies till it gets to the light gets to us. And so the distortions that we're looking at are very subtle. We can't say anything about the cosmic shear in the universe from looking at one galaxy on its own. Instead, we have to look at an ensemble of galaxies. We have to construct statistics that try to make some kind of measurement, for example, the correlations of the distortions in galaxy shapes. We're really looking at well, frankly, we're looking at big data here. We're looking at the kind of measurements that require a lot of data, because if we're just looking at a small area in the universe, then we're not going to be able to tell that much about the structure and evolution of matter in the universe as a whole. So the first observation of cosmic shear was back in 2000, but really in the last 10 years, we've seen a massive amount of work on weak lensing. So, for example, if you just do a simple search in the archive for weak lensing in the title, you get nearly 500 papers. Cosmic shear, you get around 100 papers, and those are just the papers that use these terms specifically. You know, we're talking about at least a paper a week being published on this subject. It's an enormous industry, and there's an enormous amount of really excellent work going on looking at this. And one of the reasons why there's so much attention in weak lensing and cosmic shear is because it's such a potentially powerful method to constrain these models of dark energy that we've heard discussed this morning. So I want to start off by talking a little bit about our current data sets and what we've learned from the current data sets and what the limitations are of the data. And this is a nice figure from James G, showing, sort of placing all the data sets that we have at the moment and our future data sets, placing them in terms of how deep they go and how much area they cover. And I'm going to focus on these three data sets here so far, the data set from the Canada, France, or the CFHT Legacy Survey Wide and the Deep Lens Survey. These are results that have been published in the last year or so. And I just want to reiterate that cosmic variance is an issue here. We have the current data sets, either fairly wide, fairly shallow surveys, or fairly small and pretty deep surveys. We at the moment are not sampling even close to a representative sample of the universe. We have a pretty small area that we're looking at, and so a lot of the work that's been done so far is figuring out how to maximize the information that we can extract from the data that we already have. So this is some of the constraints that we have from, as I say, from the last year or so, from cosmic shear analysis of the CFHT dataset and the DLS dataset. As I said before, the CFHT dataset is wide. When I say wide, it's 154 square degrees. In terms of what the data we're expecting to get in the future, even in the next few years, this is pretty small. And it's relatively shallow with a limiting magnitude of around 24.5. And DLS is sort of in the other direction where it's pretty deep. The limiting magnitude is around 27, but it's not very wide at all. It covers only 20 square degrees. And you can see that they have fairly similar constraints on the parameters, cosmological parameters, omega matter and sigma 8. And they have this very characteristic banana kind of shape in the contours where we have degeneracy between these two parameters. And this is something that you've seen just now from David's talk, that this is kind of a problem. And trying to understand different methods that we can use to try to break these degeneracies by making various different combinations of measurements is a really big industry at the moment in the field. They've had some really good results. What's something that's pretty interesting, I think something that's not necessarily common knowledge, is that the constraints on cosmological parameters through cosmic shear, through weak lensing measurements of cosmic shear, are actually fairly competitive with the best measurements out there from Planck at a single value of the parameters. So there are large degeneracy between the parameters, but if you can fix the value of one of the parameters, then the uncertainties on the other parameters are not so bad. So this is another nice figure from James G, showing a comparison of the uncertainties on the quantity sigma 8 at a fixed value of omega matter. So the error bars for Planck, for DLS, and CFHT are comparable. The results are not in total agreement, but the uncertainties are comparable. So really we want to think about how can we break these degeneracies, how can we be able to get this kind of a few percent level measurement on our cosmological parameters with the data that we have. And one of the things that is pretty exciting about the next 10 years of cosmic shear, and the next 10 years of weak lensing measurements, is that we have an awful lot more data coming soon. We have the DES survey, which is already started. There's a lot of people in KIPAC been heavily involved in DES and heavily involved in the commissioning for this survey. And we've got, well, the data's already coming in. There's some data in the can already. It's looking pretty good. This is a 5,000 square degree survey with a limiting magnitude of 26. It sits up here on our diagram. And then sort of looking further ahead to the maybe slightly more long-term future, perhaps 8 years from now, we'll start to have data from the Large Synoptic Survey Telescope, which is going to be very wide. We're covering the entire southern hemisphere with a deep limiting magnitude of 27.5 that will be achieved over the 10-year survey. And LSST is something that, again, SLAC and KIPAC is pretty heavily involved in. I myself work on LSST, so I'm something of a biased observer in this. But we're going to have an enormous amount of data in the next 10 years with these surveys. They're going to be both wide and deep, so we're going to start to lose the issue of cosmic variance. We're going to have a maximal amount of data, and so again, the pressure is on us as scientists, as cosmologists, to try to understand how we can best use that data, what we can do with that data, and how can we best leverage this data, how can we extract the maximal amount of information from it. Because weak lensing, as Anya pointed out, this is a tricky business. Weak lensing is a noisy business. What we're looking for is a very small signal. We're looking for a distortion in galaxy shape of less than 1% perhaps. This is a very small signal that we're trying to extract. And the backgrounds that we have to contend with, things like the distortion on an observed galaxy shape due to atmospheric effects or due to distortions in the telescope, and even as specifically as Anya pointed out, galaxy shape measurement methods, they can all introduce distortions in the galaxy shape of a few percent. And this is something that's always a bit mind-blowing to me, is that the very method by which we measure the galaxy shapes is introducing such a large distortion. It's introducing distortions in galaxy shapes larger than the effect we're trying to measure. It's something that we could surely do better at. So the question that we're working on, that people have been working on before and that we're really looking forward to working on, is how do we distinguish signal from noise? And this is something that can come into these degeneracies in parameter estimation, because as David was saying, we can combine many different statistics. We can combine many different statistics of measurement of the growth of structure in the universe, but also different statistics around gravitational lensing. We can construct many different lensing statistics, and by making combinations of these lensing statistics, we can actually do pretty well at understanding our systematic errors, because each of these statistics is impacted in a different way by these systematic errors. And also, these different statistics have slightly different sensitivities to the cosmological parameters that we're trying to measure. So we can also break the degeneracies between these cosmological parameters by looking at different statistics. And these are statistics that are much less well studied than the sort of canonical weak lensing statistic of the shear correlation function. But we've seen in the last few years much more attention being paid to them, and we're starting to see some real progress being made in understanding what these measurements mean and understanding what some of the advantages and disadvantages of these measurements are. So for example, we're very familiar with thinking about how gravitational lensing can distort the shapes of galaxies, can shear the shapes of galaxies, but of course there's also a magnification effect from gravitational lensing. And so some recent work has been looking at, first of all, how we can use a combination of magnification and shear to reduce the errors on our measurements, to reduce the uncertainties on our measurements of cosmological parameters by a factor of a few. This is a nice paper from Verbeeker from 2009 showing how making the combination, shown here in green, you can combine measurements of magnification and shear and really start to reduce the uncertainty on your parameters. And for a while, this was considered to be all very well, but magnification, cosmic magnification, is a difficult thing to measure. But then last year, using the DLS data, Chris Morrison et al. Were able to make a measurement of cosmic shear through magnification. And they came out with this very nice result that was able to put some constraints on cosmological parameters already using the DLS data, simply by being, well, not simply, but by being very careful with how they process their data, by checking out all these systematic errors, being very precise with how they dealt with their data. They're able to make now measurements of cosmic magnification, which is fantastic. Other statistics, an area that I'm particularly interested in, is looking at the statistics of peaks in the shear field. Now, when the way that we're most accustomed to thinking about a peak in the shear field is when there's a peak in gravitational lensing caused by specific objects, so caused by clusters, for example. This is something we've heard a lot about already this morning, is how clusters specifically can be used to constrain models of cosmology. But it turns out that if you're looking at the shear field and you see a very significant peak in the shear field, that's not necessarily caused by one single cluster, by one object. This can be caused by the superposition of many small objects. It can be superposition along the line of sight of many smaller clusters, or by just random fluctuations in the matter density along the line of sight. And it turns out that, of course, there's cosmological information in this as well. So by looking at the statistics of the peaks in the shear counts, in the shear field, you can start to construct statistics of that will constrain cosmology as well. And this has become sort of a little mini industry in the last 2 or 3 years. There's been starting to be quite a few papers coming out looking at this method, looking at how successful it can be in constraining cosmological parameters and how it can also be used to break degeneracies between parameters. I just want to point out something that I specifically was looking at, is that this is a method that's relatively insensitive to measurement errors. It's relatively insensitive to issues around the distortion that's introduced by atmosphere, for example, or by telescope optics. We see that there's almost no effect on the constraints that you can obtain on cosmological parameters due to your to issues with the atmosphere or the telescopes, which is really encouraging. But there's a lot more work yet to be done on this field. And just to sort of bring home this point that by combining lots of different lensing statistics, we can really start to nail in on the cosmological parameters. I want to show these figures from this really nice paper by Stefan Hilbert et al. From earlier this year, showing that by combining different weak lensing statistics, you can really reduce your uncertainties. And not only that, but you can really reduce your degeneracies. And this is, it's not blown up terribly well, but this is the constraints on sigma, on sigma 8 and omega beta for the traditional kind of weak lensing statistic, the shear correlation function alone in blue, from the statistics of peak counts in green, and then and also the aperture mass statistic in red you can barely see on this figure. But then the combination of them in black, I mean, this is very encouraging. Just by combining different statistics, different measurements of cosmic shear, you can really start to break some of the degeneracies. And then when you start to combine it with other measurements of other dark energy measurements, then it's really exciting to think what we might get out of this in the next few years. So the current data sets that we have, they're already providing constraints on dark energy parameters that are really interesting. Combining these measurements in lots of different ways, combining the different statistics, combining the different types of measurements, and in that with the very large data sets that we expect to have in the next few years, well, that's also very promising, it's very exciting. This kind of explains why there's been so much excitement surrounding measurements of cosmic shear and surrounding the possibilities of cosmic shear being really able to constrain our models of cosmology. This is a paragraph I lifted from the Dark Energy Task Force report from 2006, saying that it's likely to be the most powerful individual stage 4 technique and also the most powerful component in a multi-technique program. And I could stop right there. I could end on a nice optimistic, happy note, you know, big smiley face. This is really promising. We've got some really interesting times ahead of us. The next 10 years are going to be fantastic. But there's always a caveat in this kind of thing. The caveat here is that the weak lensing measurements are limited by systematic errors that are difficult to predict. And this is where I take a slightly negative tone of voice. And the rest of my talk, I want to go over some of these systematic errors that we're starting to look at and that we're starting to be concerned about, that we're starting to develop some techniques to mitigate and to understand these systematic errors. Because this is where we're going to be brought back down to ground, where the limitations of cosmic shear measurements are going to become apparent. So there are a lot of weak lensing systematic errors. Anya mentioned this again earlier on, that there's a lot of problems. And with cosmic shear, we care about understanding these systematic errors to an exquisite level, typically to the sub% level. We want to be able to understand these systematic errors to a very high level of accuracy. And I'm going to go through a few of these, what I've listed here in the next few slides. And I want to point out that these systematic errors have always been there. These aren't new systematic errors that we're suddenly discovering that are coming into our data now. These are uncertainties and issues that have always been there. But when we've had this much smaller data sets and the much larger uncertainties due to cosmic variance and statistical error, these systematic uncertainties were much less important. But when we have these beautiful big data sets coming up, when the statistical error is going to be tiny, then we're going to really need to understand our systematic errors if we want to get the maximal amount of information from it. So how can we study these systematic errors? Well, this is something that those of us at SLAC and around the country who are members of the LSST Dark Energy Science Collaboration, this is what we're looking at. This is one of the main reasons why this collaboration was formed now, so far in advance of the data coming in. Because we need to start looking at these systematic errors. We need to start understanding them. We need to start figuring out what we can do about them. And so a lot of the work that I'm going to present just in the next couple of slides is done as part of the Dark Energy Science Collaboration. With this aim in mind. So just start off by the sort of traditional sort of systematic errors that we're all familiar with, that we all have worked on, well, all of us who are involved in making measurements of weak lensing, things that we've tried to understand and correct for. So one of the most important of these is effects of the PSF, because I remind you, we're looking for a distortion in galaxy shapes that's of a % or less level. And so when we have distortions introduced by the atmosphere on the telescope of an order of a few %, then we want to really understand how this works. And so a former grad student here, Chiwei Chang, who just left just a couple months ago, graduated, she's looking at, specifically for LSST, what kind of level are these effects going to be at? not just the ellipticity. This figure here shows the effect of the galaxy ellipticity of these different effects, but also how this looks when you're looking at, for example, the shear correlation function, what kind of impact this has. And it turns out that for LSST, this is at a manageable level. You know, we've got a correlation function level of around 10 to the minus 4 for a lot of these PSF systematic effects, which is reassuring. That doesn't mean that we can't do, that we should ignore this and do nothing about it. This is a great first step in trying to understand what the effects are. And then more work done by Chiwei and also done by Phil, looking at how do we interpolate the PSF? It's not enough to just know what the PSF is. We measure the PSF using the stars in the field. We don't have any control over where the stars land in a field. Typically, we have perhaps 1 star per square arc minute, and we're looking at having maybe 30 or 40 galaxies per square arc minute in our measurements with LSST. And if we have that kind of sampling, then how are we going to be able to interpolate the PSF parameters that we've measured at the locations of the stars? How are we going to be able to interpolate that out to where the galaxies are, where we actually need to know the PSF in order to deconvolve it from the galaxy shape? This is work done by Chiwei looking at a new method of doing this kind of interpolation. Because with LSST specifically, we're going to have 15-second exposures. This means that the PSF is not very smoothly varying over the field of view. So looking at different methods of how we can interpolate the PSF, and you see that there are improvements to be made, is what I'm trying to say here. This is one of the areas in which improvements are being made and can be made further to get a more intelligent way of interpolating the PSF. And there's also work being done here at KIPAC by Josh, who will, I'm sure, be happy to talk to you more about this later on. If you're interested, looking at chromatic effects, there is a whole host of chromatic effects, again related to understanding the PSF and understanding its impact on galaxies, because there are all sorts of different effects related to the fact that stars have often a very different SED than galaxies. And so if you have a PSF that depends on the colors of your object, which is, there's a lot of effects that can come in and impact that. If you're not correcting for this, then you can end up with a significant impact on your galaxy shape. If you're using a star with colors that are very different to your galaxy, then you're not going to be accurately measuring the PSF of your galaxy. The last thing that I really want to mention here is in terms of some systematic studies that are being done at the moment, involves blending. This is work done by David Kirkby and his group down at UC Irvine. Deep surveys have a particular problem in that they have a lot of overlaps. There's a lot of galaxies in our field of view for LSST, and quite a lot of them overlap for what we consider the gold weak lensing sample in LSST, which has a limiting magnitude of around 25 in the I band. We have a raw galaxy density of around 55 per square arc minute, of which 50 to 60% of them are overlapping. And so how do we deal with this? I mean, what do we do with this? Do we figure out some way of de-blending these galaxies? Do we just mask out all the blended galaxies? There's a lot of subtleties in this. And even it turns out, even if we can mask all the regions that are overlapping, that means the effective number of usable galaxies reduced from 42 to around 26 per square arc minute, which is that makes an enormous impact on the available statistics of our measurements. It's equivalent to roughly a 95% loss of exposure time, that's not great. I mean, the whole point of having these new data sets, of having these new surveys that are wide and deep, is that we have so much more data to play with. And if we have to throw out most of this data because we have got issues with masking and other things, then it's just not good enough. So this is more work that needs to be done in the next 10 years to do better than simply masking out blended regions. And I'll skip over the last couple of things. So the prospects, in my view, for the next 10 years of cosmic shear is that we're going to start to have really the lensing big data. The statistical error and cosmic variance are no longer going to be the limiting factor in our measurements. We've got the data from DES and LSST. It's tremendously exciting to have this amount of data on the horizon. and to know that we've got the possibility of really understanding something about the evolution of the universe and dark energy through this. But I predict that in the next 10 years, we're going to be spending more and more of our time thinking about systematic errors, really getting down to the nitty-gritty of this, you know. We're going to be getting our hands dirty. We're no longer going to be publishing the easy papers of the nice measurements that, you know, that take some time to understand, but where you can neglect a lot of these kinds of systematic errors. We're going to have to be spending more and more of our time understanding our data, which is going to be very exciting for people like me who really enjoy understanding data. But I think that this comes back a large, and so some of the things that we were talking about in the unconference yesterday afternoon were, you know, with this fantastically complex whiteboard of the graphical representation of the problem is where we start off and where we start thinking about these problems, where we start coming up with new ideas of how we can solve or mitigate these problems. And I want to sort of point out that a lot of the things that I'm talking about here, a lot of things that I see are going to be exciting opportunities, shall we say, in Cosmic Shear. A lot of the things that we were discussing in the big data session yesterday morning, there's a lot of parallels in dealing with very large data sets, dealing with very large simulations, dealing with machine learning. All these kinds of techniques are going to be coming into how we deal with cosmic shear measurements in the next 10 years, which makes it very interesting. And so I'll just put my summary up there and ask if you have any questions.
It's one of the interesting things is so many of the issues about understanding the PSF relate to the fact that the stars are different from the galaxies, and the stars are sparse on the CCD. But given that LSST and many of these missions are going to be taking many images through different conditions, can't we just get the PSFs from the galaxies themselves?
That is, it's possible. So there's two things we can look at there. One is looking at unresolved galaxies, galaxies that we're not necessarily going to want to use for making weak lensing measurements because we don't, you know, they have too low signal to noise. But there's information about the PSF in there specifically, which we can look at it sort of in that way. But then in the same sense, in the other direction, then yes, you can, why not look at all the galaxies and look at the PSF directly from the galaxies? I'm unaware of attempts to do that. I'm quite sure that people have thought about that, but I'm unaware of, does anyone know of specific attempts to do that? I don't see any reason why it would not work.
We find in our own work that we can't see the PSF resolved.
It would be fantastic. Right. It would be fantastic to be able to do that. It would solve a lot of our problems if we could.
Thanks a lot. And since we are running a little bit short in time, we can thank Debbie again.